Okay, let's move on to the next chapter, chapter 23, carbonyl alpha carbon reactions. Let's do a little review. Recall when you have an aldehyde or a ketone and you attack it with a nucleophile followed by aqueous workup, the nucleophile attacks the carbonyl carbon, you end up with the alcohol nucleophilic addition. No new news there. If you have an RCOZ, however, recall the nucleophile is going to attack the carbonyl. Double bond breaks, pi bond reforms, kicks off Z. The nucleophile is going to end up on that carbon. Because he's a good nucleophile, we get nucleophilic acyl substitution. Did a whole bunch of that. But there's another reaction we can get here also. If you have a carbonyl and the alpha carbon, alpha to the carbonyl has a hydrogen on it, it turns out this hydrogen is a little bit more acidic than you'd think it would be. Why is it more acidic? Because recall that this is a ketone, and anytime you have the ketone, it is in equilibrium with its tautomer, the enol. Recall we can take this hydrogen, move it up here, take the pi bond, move it down there, and we get this enol here. And that, in the enol form, this hydrogen is easier to lose. So you take away that hydrogen, you end up with this enolate anion. Note that the negative charge is on this oxygen. With this enolate anion, move the pi bond, reform the pi bond between the carbon and the oxygen, and take this pi bond, move it on the carbon. There's resonance form between the negative charge being on the oxygen and the negative charge being on that alpha carbon. Because of this resonance, this proton is easier to lose, and it turns out that when we look at its reactivity, it's going to react as this carbanion right there. That's going to be its reactivity, these enols and these enolate anions. So let's look at these enols a little closer. We went through them in Organic 1, so this should be kind of review. That if you anytime you have a ketone, you can take an alpha hydrogen, move it up here, move the double bond here to get this enol. Recall an enol, anytime you have a carbon that is both part of a double bond and contains an OH on it. Recall these are called tautomers. The process is tautomerization, and recall the keto form is almost always more stable. In cyclohexanone, this equilibrium is constantly happening, but 99% of the cyclohexanone is in the keto form, less than 1% is in the enol form. Keto form is more stable. Note, check out this guy down here. If you have a ketone, note it's an unsymmetrical ketone, this isopropyl methyl ketone right here. Still, you've got alpha hydrogens here. You can form an enol form with a double bond here, or an enol form with a double bond here. Here are those two. These two combined still make up less than 1% of this stuff at equilibrium. It's just the keto form is just so much more stable. But then someone said, okay, well, but can we push it? Turns out, of course, this is chemistry. Anytime someone says you can't do that, someone makes it their life's mission to do it anyway. So let's look at this molecule where you have a bicarbonyl compound, dicarbonyl, where you've got CH3, C double bond O, CH2, C double bond O, CH3. It has this is the keto form. It has the enol form where you just take this hydrogen here of the CH2 and move it to one of these carbonyls. Let's move it to this one up here. And so this hydrogen gets moved to this carbonyl. The double bond gets put right there. That would give us this beast right here. Note it is conjugated, double, single, double bond. That adds stability. Also note this hydrogen could have, instead of going onto this oxygen, could have gone over to this oxygen over here, and we get this thing right here. Note this is a 6-membered ring, and we have an intramolecular hydrogen bond forming to make this 6-membered ring. That's actually a fairly stable beast. Also note that technically this is not resonance. When you look at these two structures, they look awful similar. It seems to me that the only difference is the double bond is here versus over here, or at the right oxygen compared to the left oxygen. That's just moving electrons. The difference is, technically, here's the hydrogen bonded to this oxygen, where over here the hydrogen is bonded to the left oxygen. So that's what does not make these resonance forms, because this hydrogen has shifted its bond. It's bonded to the right oxygen here, it's bonded to the left oxygen here. Technically, we've broken a single bond, so these are not resonance forms. But truthfully, they're awful close. I mean, this is just a hydrogen bonding interaction here. We've just gone from a hydrogen bonding interaction to an actual bond there, and the hydrogen didn't actually move very much. So they're very close to being resonance, but it is not resonance technically. But what ends up happening is when you look at these two beasts, they're pretty stable. So it turns out for this molecule, it really doesn't exist as this. Only 24% exists in this keto form. 76% is in this enol form right here. All right. There's an experiment we can actually do on our instrument, because it turns out that if you run the NMR, you can actually see the keto form and the enol form. You can see this as a CH2, or you can see the proton up here. Because of the ring structure and everything right here, and the two oxygens, this hydrogen actually comes at about 15 ppm. That's pretty far downfield. All right, so let's look at the mechanism of tautomerization. How does the molecule go from the keto form to the enol form? Turns out it's actually fairly slow, so you need to have a catalyst in there. Let's start with an acid catalyst. If we have this beast here, we've seen this before. We got a carbonyl. Carbonyl attacks a hydrogen of a strong acid to make the conjugate base water here. Have this protonated guy, which is in resonance with this, which means it's stable. So we've protonated that oxygen, and then our water can come back in and take that hydrogen to make our enol form. And our acid, we get it back. It's the catalyst. Note, very important here, it's really not this specific individual hydrogen that ends up here. The hydrogen that ends up on that oxygen came from the acid catalyst. This hydrogen ends up back on the acid catalyst. So the net result is this hydrogen was here. There was a hydrogen on this carbon. There's now no longer that hydrogen there, and there's now a hydrogen up there. So it looks like this hydrogen kind of moved up there. That's not really what happened, but that's the net result. One less hydrogen on this carbon, one more hydrogen on that oxygen. Who cares where they came from? The net result is, looks like this guy moved up there. Note, acid, catalyst, protonation, then deprotonation. Of course, if you've got acid, the bases get a little bit jealous and say, hey, well, maybe we can do it too. In this case, we can't have this oxygen attacking this hydrogen. These are both negatively charged beasts. So the hydroxide will attack this hydrogen to make water. The bonding pair will break to become a lone pair on this carbon, making it a carbanion. This has a resonance form. We can move this lone pair here to make a double bond, and then this double bond breaks to make that negative charge oxygen, which then snags a hydrogen off of the water, and we ended up with our base back again, along with our enol form. Note, in the base method, based mechanism, it's deprotonation first, then protonation. Now, there looks like there might be a chance, hey, is this hydrogen the one that actually ends up on here? Because the hydroxide takes it to make water, and then this guy takes it from water. The chances that this hydrogen here that gets attacked by this oxygen was the very same one that came off that very same molecule. That's not the highest chance, but who knows? The point is, we don't care. It's just a matter of, hey, the base was in there, we got it back, it's a catalyst, a hydrogen was here, now it's up there on the oxygen. All right. Enols, and especially enolate anions, are electron rich, so they are going to react as nucleophiles. An enol plus an electrophile will form a new carbon electrophile bond at the alpha carbon. So here's what we're going to be kind of looking at here. If we've got our keto form, we know tautomerization makes it the enol form, which is the more reactive form. Note, it is the less one we have at equilibrium because it's higher energy. Higher energy means more reactive, so the enol form is a more reactive form. Through resonance, that means we've got a negative charge on this carbon here, making it a very nucleophilic carbon, a carbanion in this resonance form. And it will attack the electrophile and will put the electron up here. Deprotonation gets rid of that proton up there. Net result is this was a proton. Now it is the electrophile. We've kind of substituted off a proton at the alpha carbon for an electrophile. All right. Now, if you want the reaction to run a little bit better, instead of using a resonance form that has a negative charge on that alpha carbon, why don't we just add a base that will take off of that alpha carbon's hydrogen? Just add this base here that will remove that hydrogen, and then we get the negative lone pair on this carbon, which is in a resonance form with this enolate. But note, these are both resonance forms, and this is the more reactive resonance form. Carbanions are more reactive than oxides. So this is a more reactive resonance form. So a lot of the time when we add a base to take that hydrogen, we are going to write it as the carbanion form because that's how it reacts. Well, what type of base do we need to do this reaction? How acidic is this? Now your first thoughts is, okay, this is a hydrogen on a normal carbon, pKa of around, I don't know, pKa of around 50 or so, right? But then the truth of the matter is, in the enol form, this hydrogen is up here. It's a hydrogen on an oxygen, which is a pKa of closer to 17, 16. It turns out, because of that enol tautomerization, the pKa of the protons alpha to a carbonyl is about 19.2. That's fairly darn acidic for protons of a methyl group, or protons of a methylene, a proton just bonded to a carbon. All right, why are these so acidic? Well, just like we talked before with the enolate tautomer form, plus when you take that proton off, you've got resonance. We have the carbanion resonance form. This is actual resonance form now, not tautomerization, because all we're moving is electrons. There's no hydrogen moving at this point. So these are resonance forms, and resonance makes it more stable. The product, our reaction, has resonance forms. The reaction goes further than we thought it would. All right. Note, with a pKa of 19.2, that means it's more acidic than terminal alkynes would have a pKa of 25, but not as acidic as alcohols. But alcohols are 16 to 18. This is 19. They're pretty similar in acidity to alcohols. Perhaps we can use that knowledge in the future. All right. So then, here's an example reaction here. Just add the base. You snag one of these hydrogens. There's your resonance forms. What base is going to work? Good news. If you know chapter 2 really well, you could probably tell me bases that might work. Recall, for acid-base reaction to work, for a base to come in and snag this proton, the product H of this reaction, the HB, the conjugate acid of this base, its pKa must be higher than the pKa of our original acid. So these have a pKa of 19.2, which means the base we want to use, its conjugate acid must have a pKa larger than 19, and which means methoxide won't do it, because methanol, pKa of like 15.5. Ethoxide really isn't going to do it very well, pKa of 16. If you added ethoxide here, the conjugate acid would be ethanol. pKa of 16 would be the conjugate acid over here. whereas this has pKa of 19. That reaction doesn't go very well, but it will go a little bit because 16 and 19 are fairly close. So the bases we're going to choose, alkoxides won't do it. NaH is a good one because the conjugate acid of H- is H2, pKa of 35, so NaH is a really nice one. We're going to find there's another nice base we're going to use quite a bit. It's a bit on the expensive side, but LDA, lithium diisopropylamide, got a nitrogen with 2 isopropyl groups on it, negatively charged. Recall, NH2- is a very strong base. Its conjugate acid is NH3. NH3 has a pKa of 38. This is very, very similar. Instead of NH2-, it's NR2-. We're going to find out in a couple chapters that the more R groups you have on a nitrogen, the more basic that nitrogen is. So instead of a pKa of 38, this beast has a pKa of 40, very close to 38. Either way, it's a very strong base, just like NH2- is. However, we got these 2 isopropyl groups on it, which add some steric hindrance to this base, which means it's not going to be a good nucleophile. Yay for that, because then we can just make sure it reacts as a strong base and will not attack carbons like a nucleophile would. Note, there are other enolates. Anytime you have carbonyls that have hydrogens on a carbon alpha to the carbonyl carbon, you can get enolates. So we can get ester enolates right here. Those are possible. Note, with an ester, the pKa of these 2 protons isn't 19, it's about 25. So still within reach of LDA or a nice strong base like sodium hydride. Other enolates that we find, we can get enolates from nitriles. If we've got this nitrile here and we've got a carbon with a hydrogen on it that's alpha to the carbon of the nitrile, that's pK of 25 also, so we can get enolates there. Pretty wacky resonance right here where we get the negative charge on the nitrogen, but makes sense because in a normal enolate, the resonance has a negative charge on the oxygen, just on the nitrogen here. These are fun. These beta dicarbonyl compounds, we're going to do a lot with this, some really fun stuff. Where if you have, we've seen it before, CH3, C double bond O, CH2, C double bond O, CH3. Note that the enol form of this compound is more stable, which tells us that hydrogen is probably more easily snagged. It turns out the pKa of the hydrogens on the CH2 is a pKa of 9, which means our base doesn't have to be very strong. Sodium hydroxide or sodium methoxide is just going to do a really good job of taking off one of these hydrogens to make this enolate product. Why is that? Well, because this has a resonance form to this enolate, which has a resonance form with this enolate. No longer tautomerization because we are not moving that hydrogen. There's no hydrogen here to move back and forth. So this is purely resonance. 3 resonance forms, nice and stable. All right, we will start looking at reactions of these in the next video.